All right, we're doing problem 7, and this starts off by giving us the Maclaurin series for e to the x, which is one of the ones we have memorized. The continuous function f is defined by this. You can see they've sort of built upon this e to the x function. F of 1 equals 1. The function has derivatives of all orders at x equals 1. So let's see. Part A says write the first 4 non-zero terms and the general term for the series for e to the x minus 1 squared about x equals 1. You don't have to force this center to happen. This will happen by default because all of our terms will have an x minus 1 in them. All right, so we're not doing the full f of x for part A. We're just subbing in x minus 1 squared. So e to the x minus 1 squared just means I can take my original e to the x and I can build upon it by plugging in x minus 1 squared. So 1 plus x minus 1 squared plus, when you square x minus 1 squared, you're going to get x minus 1 to the 4th over 2 plus x minus 1 to the 6th because it was squared to the 3rd over 6 plus dot 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 plus. So these are the first 4 non-zero terms. The general term is plugging in x minus 1 squared and raising it to the n power, which just multiplies that exponent, over n factorial, and make sure you allow this to be infinite by adding the plus dot 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 at the end. So that's it for part A. For part B, use the Taylor series found in part A to write the first 4 non-zero terms and the general term of the Taylor series for f. Remember, f is this thing, about x equals 1. So do this in stages. E to the x minus 1 squared minus 1 should be addressed first because order of operations, you do that math first in this fraction if you're plugging numbers in. Now, if you subtract 1 from the above function, all it would do is cancel out the 1. So this would start at x minus 1 squared plus x minus 1 to the 4th over 2 plus x, oh no, not to the 4th, sorry. Oh, no, yeah, sorry. I don't know what I'm doing. Okay, so all I did was subtract the 1 off. Sorry, I was a step ahead of myself. Times x minus 1 to the 6th over 6. Now, we don't have 4 non-zero terms here, so let's get one more. What would the next term have been? So our exponents are going 2, 4, 6. Next one would have been x minus 1 to the 8th. And remember, this is over n factorial. This would have been when n equals, let's see, 1, 2, 3, n equals 4. So 4 factorial is 24. Or you could just keep it as 4 factorial. Plus dot 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 plus. There would still be this general term. Subtracting the 1 doesn't change the fact that this general term is in there somewhere. It might not be at the same number n that it was back here, but that's okay. And then the last step is to make this truly f of x. Now we need to divide all of those terms by x minus 1 squared. So just the finishing piece here. So if we divide every term here by x minus 1 squared, we're back to getting 1 plus x minus 1 squared over 2 plus x minus 1 to the 4th over 6 plus x minus 1 to the 6th over 24 plus dot 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 plus x minus 1 to the, now you can make this 2n minus 2, that's what we're doing, over n factorial. I wouldn't simplify that as I wouldn't say, it's not wrong to say x minus 1 to the 2n over x minus 1 squared. That's fine too, but I like to subtract my exponents like that. Or you could also just look for a new pattern here. So you could also say, well, here this is sort of like when n equals 0, 1, 2, 3. You could also say that this is x minus 1 to the 2n. And then instead of n factorial down here, this is 2 factorial, 3 factorial, 4 factorial. So this is like n plus 1 factorial. So it doesn't matter. Either one of these general terms is fine because they both exist somewhere along the way, and they're both equivalent. All right, so pick your favorite general term, basically. All right, what else do we have to do with this? I'm going to sort of temporarily leave this here in case it's going to be nicer to work with this one. So for part C, use the ratio test to find the interval of convergence for the series found in part B. All right, so the ratio test is taking the limit as n approaches infinity of the general term. So let's just go off of the original, assuming that we're not going to use our pattern here, or our simplified pattern here. So maybe you don't want to worry about finding a pattern every time if you think that's hard. You can still just say n plus 1th term over nth term. So let's go with the original and say if we plug in n plus 1, we get 2n plus 2 minus 2. So we get x minus 1 to the 2n over n plus 1 factorial times the nth term would be n factorial over x minus 1 to the 2n minus 2. So simplifying that is a little ugly because of the negative exponent. So that's where maybe you use the original pattern. That might make your life easier. But it's not too bad. If we subtract these exponents, we're left with a negative 2 in the denominator, or we could say 2n minus the quantity 2n minus 2. Leaves me with x minus 1 to the 2nd power in the numerator. And the n factorial cancels with the n plus 1 factorial to just leave us with n plus 1. Right? And when we take that limit, we get 0, which is always less than 1. So this series converges to f of x by the ratio test for all x on the interval negative infinity to infinity. All right, and part D says use the Taylor series for f. So again, use this thing. To determine whether the graph of f has any points of inflection. So how do we, this is way back to like chapter 3, how do we determine points of inflection? There are points of inflection if the second derivative changes signs. So we need a second derivative. We have f of x. If you have terms for f of x, it's always easier to not go about writing the series, just take the derivative of the terms, including the nth term. So let's start there. Let's get the first derivative of x to begin with. So f prime of x, the 1 goes away. We get 2x minus 1 to the first over 2. I'll simplify this later. Plus 4x minus 1 to the third over 6. Plus 6x minus 1 to the fifth over 24. Plus dot 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 plus. Now, which one do we want to use for our derivative? Maybe we use this pattern. I don't know. I guess if I use this one, if I use this one for part C, I should probably assume I haven't made this one yet. But I bet it would be easier to use the pattern one. But it's fine. We can go either way. So let's pull our power down. Subtract 1 from our exponent. 2n minus 2 minus 1 is 2n minus 3. N factorial is still there. Plus dot dot dot. Now these do reduce, and I'm going to do that because I need to take a second derivative, so why complicate things? So how about I just rewrite this so it doesn't get ugly? So this is really x minus 1 times 2x minus 1 cubed to the third plus x minus 1 to the fifth over 4 plus, how is this going to simplify? I'm not going to reduce the nth term because it wouldn't simplify a ton and I don't want to screw it up. All right, let's take the second derivative. The derivative of x minus 1 is 1. This becomes 2 times 3 over 3, so this becomes 2 times x minus 1 squared. This becomes plus 5 x minus 1 to the fourth over 4 plus dot dot dot. 2n minus 2 times 2n minus 3 times x minus 1 to the 2n minus 4 all over n factorial plus dot dot dot. Now remember, the reason we want to have a second derivative is normally we want to be able to talk about whether or not the second derivative changes signs to find points of inflection. So remember, this converges for all x, so we're not limited to that. No matter what x you plug in, what's going to happen on every term? We're raising to even exponents only. 2n minus 4 is always even. So all of those terms are positive. All of these coefficients, 2n minus 2 times 2n minus 3 over n factorial, all of those are going to be positive when you multiply them through, right? Because assuming that our n starts at, I guess it could start at 1, you would get 0 times a negative, or 2, you're going to start getting positives out here. So f double prime of x is always positive, or you could say, let me shorten this up, f double prime of x is greater than or equal to, I guess, 0 for all x. So f of x is always concave up. That means that there are no points of inflection. Make sure you answer the actual question that was asked. There are no points of inflection for f of x.